Alright, so we have done differentiation in mathematics, okay, so what did we need to have set ready in mathematics so that we can differentiate?
Y squared.
Sorry?
Y squared is y.
As in the subject of the equation, okay, so we need y, the subject equation, in be able to differentiate. What is the graph of that equation then? It's a circle, isn't it? Okay, so because it is not a function, okay, a circle itself is not a function, okay, I can't just differentiate that using your mathematics skills because you got it fails vertical line test. Now for this one, I can actually rearrange to get y the subject, okay, however I'm going to have two different equations because of the square root. You're going to have plus or minus the root, and thinking about your semicircle, okay, as part of your graph, and then you have to differentiate that in order to find the equation of the first derivative. Okay. Now, what implicit differentiation allows us to do is when we have that problem where we don't have y as the subject, okay, we can follow this technique. All right. So, if I differentiate everything with respect to x, okay, so put a d dx in front of each of those terms in the equation. Okay, so when I've got some function of x, so I've got x squared here, to differentiate that is not an issue, okay, because we are differentiating with respect to x. So this will be 2x when we differentiate. Okay, however, this is a d dx of y squared, so I am differentiating the independent variable. Alright, when I do that, I can write 2y, but because I differentiated y with respect to x, after that I'll need to write dy dx. Because I differentiated something in terms of y in respect to x. Okay? Equals, and what's the derivative of 1? 0. Okay, so it's equal constant number. Right. So this is how you're going to find dy dx by implicit differentiation. So now what we need to do is get dy dx the subject of the equation. Okay, so dy dx equals, so I need to bring this over to the other side, negative 2x. Okay, and then I've got to divide by 2y because that's what I'm multiplying by. Okay, so I've just done a two-step equation in one step. Okay. Okay, so it equals negative x on y. Okay. Now, what this allows us to do, that if you pick a point on your circle and substitute that point into here, that will give you the gradient of the tangent at that point with dy dx. Okay, so let's looking at the graph. Okay, so that's the circle, x squared plus y squared is 1. Right, if I pick this point here, okay, so there's the coordinates here from GeoGebra, draw the tangent, there's the equation y equals mx plus b. Okay, so if I substitute this point for x and y into that previous thing, so dy dx is negative x on y. Okay, at this particular point, by substituting that, I should get negative 1.89 for dy dx. Okay, so equals negative 0.88 over 0.47. Substituting for x and y. Okay, put in your calculator, do I get approximately negative 1.89? Should. Let's verify it though. Because this will be rounded. That's a rounded answer, and that's also a rounded answer to test places, okay? So we're approximately something around negative 1.89, okay, from the graph. Right? And this is what implicit differentiation allows us to do. Okay, so when we can't have, when we don't have a y equals some function of x, we can manipulate it using the chain rule that I was just talked talked about in a previous mathematics lesson, to be able to calculate the gradient and tangent at any point. Alright, let's turn it on. Right, so we've got x squared plus y squared plus xy is equal to 1. Okay, so this is not a y equals some function of x, so I'm going to have to use my implicit differentiation process. Right, so just to get the understanding, right, so we need to write d dx of each term. Right, so when I've got something in terms of x, I can just differentiate straight away, the 2x. But when I've got a d dx of a function of y, okay, I can differentiate assuming it is y, but I actually have differentiated with respect to dy dx. Okay, so I need to write, when I have a y term variable, I need to write that. Alright, this next one. d dx of xy, because both the dependent and the independent variables there being multiplied with each other, I actually need to use the product rule. Okay, because these are your two independent terms, which changes because of the layout of the graph, the dependent and the independent term. So, the product rule. The second times the derivative of the first. Okay, so we've got y times 1, okay, because we've differentiated the derivative of, we have the derivative of the first term, so we've just got the y. Plus the first times the derivative of the second. So we've got x times the derivative of y. So the x, differentiate y, we have 1, so it'll be 1 lots of dy dx. Which equals the derivative of a constant number, which is 0. Okay, so once you've done that, you need to get dy dx the subject of your equation. So 2y plus x, factorise the dy dx out of that. Okay, and then you've got the 2x and y. On this side, remember the other side becomes negative. I've just left it as factored form like that. Alright. So if I pick any point x, y on the graph itself and substitute into that, it will give me the derivative. It will give me the gradient of the tangent at that particular point on the graph. Right? Now before I show you, any ideas what that graph would be? Is it? Got an xy term included there as well. Good. Like a skewed ellipse. Okay? Right, so there's the equation. There's a point. Right, and there's the gradient. So let's verify that using that point. So dy dx. 2. Okay, so at 1, 0, dy dx is going to be negative 2 lots of 1 plus 0 over nothing plus 1, which is negative 2. Okay, and that's the slope of the tangent at that point. Alright, so we're following what's going on, how to work it out. Good. Because this will be useful for the third thing I need to show you today. Okay, any questions there? Right, next one. More of a challenge. And it will be because you actually know how to differentiate sin x shape. Close. Okay, so you've got x's and y's. Okay, so we need to do a dx of x cubed y squared is equal to dx of sine of x. Okay, so you've got both the dependent and the independent variable involved there. Okay, so I have to use the product rule. Alright, so it's the second times the derivative of the first. So it'd be 3x squared y squared. Okay, plus the first times the derivative of the second. So it'd be 2x cubed y. And because we had to differentiate something involving y, I need to write after it dy dx. Alright, so I'll just move that 2 right down the very front. And you actually don't know what the derivative of sine of x is, do you? Any guess what it would be? Okay, and that will be verified early next week in mathematics. Right, so again we get dy dx subject. So dy dx is going to be cos of x. Take away 3x squared y squared all over 2x cubed y. Okay, doing a two-step equation in one step. And you've got some fascinating thing happening there. It's almost 4 hyperbolas, like 2 hyperbolas in one. Okay, because this sort of thing mirrors on the other side. Okay, and when we do extension to graphs, we'll be able to learn techniques to be able to do something of this nature. Alright. Okay, so a point C on the graph has that coordinates there. And the tangent at that point, the gradient tangent is 2.45. So let's verify from that. That's what we get. Okay, and this is why we use this process to be able to do something, so we don't have to get y the subject and then do other bits and pieces to it. Okay, just take this approach. So 0.65 and negative 1.48. Okay, so at 0.65 negative 1.48 dy dx is equal to cos of 0.65, take away 3 plus 0.65 squared, negative 1.48 squared, all over 2 lots of 0.65 cubed. Am I missing y? Negative 1.48. Okay, so this is a radian calculation. Okay, you can remember radian is also specifying distance, or specifying the distance of an arc. Alright, so that's why you need to have in radian. Alright, let's put that in the calculator and verify that we should get something close to 2.45, reading the graph that I've put together in GeoGebra. Okay, so each of these calculations, GeoGebra is 2 decimal places by default, okay? So of course we're going to have a slight rounding error, but we've got the correct answer, okay? Alright, so this is important because the next thing I'm about to show you today is going to be finding the gradient of the tangent from normal to your ellipse, and we need to use this skill so we can find that, okay? Any questions so far? Right, let's step it up one more gear so that you are familiar with the approach. Now there were issues with this particular graph that I'm still getting my head around, okay, because I had not had consistent answers even though my first derivative was correct, my rearranging to get y, the subject was correct, but when I did this sort of process with the graph, it wasn't consistent, and I'm still trying to verify why that's the case. Anyways, we're just going to focus on the implicit differentiation. Okay, I'm just going to write the third as the power. Alright, just so I can memorize my rules for differentiation. Right, so we need to do a ddx of everything there. Right, so I've got my x term here, so I can just differentiate as normal. Right, so ddx of a constant number. Okay, so it has nothing to do with x's and y's. Right, so I can just say it's 0. Now, ddx of x squared plus y squared all to the power of a half. Right, so this is your function of a function. Okay. So you bring down the power, take 1 off the power, then you have to multiply by the derivative inside the bracket. Okay, so the derivative of x squared is 2x with respect to x, the ddx of x squared, and then you need to do a ddx of y squared because you need the derivative of that. So I've differentiated something in terms of y, so after it I need to write dy dx because that's what I have differentiated with. Right? So it's really an application of the chain rule. Right, so this has a factor of 2, 2 and 2 if I were to factorise out, like so. So 1 equals x plus y dy dx all over x squared plus y squared to the half, just applying my index law there. Right, so now I need to get dy dx as subject. So the first thing I'm going to do is remove the denominator. So the square root of x squared plus y squared, so just writing that back in third form. Take away x, so I've got cross multiply that up here, bring the x on the other side, then I've got a y dy dx, so everything needs to be divided by y. Okay. Now, there are some redundancies, and I'm still working through that with the graph itself because I'm not getting consistent answers. When I get something clearer, I'll then show you what the graph looks like. Had about 3-4 pages of scribbles trying to work this thing out yesterday afternoon. Anyways. Right, so that's implicit differentiation. Any questions on that?